So we introduced the normal distribution yesterday. What we really want to do is standardize it. Bring it back to that standard normal distribution. So Z, hence why they're called Z scores, because Z is the random variable we usually use with this. And we want to get it to that standard normal distribution where the average is 0 and the variance is 1. And I mean, if the variance is 1, it also means the deviation would be 1 as well, because square root of 1 is 1. The formula, remember, is this. There's our cumulative distribution formula. So how do we do it? If I was to substitute in Z on sigma for Z, if we go back to our curve sketching ideas, that's going to create a dilation. And so we'll end up stretching our graph horizontally by a factor of the standard deviation. The equation would then become that. Now, we have a problem though, because remember, we wanted the area under the curve to always be 1, because we wanted the sum of the probabilities. If I'm now stretching this graph, I'm changing its shape. So the area is also now being affected by this factor. Now, there's the original one. Hopefully this explains it. So imagine the area is this rectangle, base times height is 1. We know its area is 1. But it's now going to become that. And actually, no, that doesn't equal 1. It will now equal sigma, our standard deviation, because we've multiplied the b, if you like, the breadth of it, by sigma. We need to get it back to 1. Well, how do we do that? We'll apply another one, which will now stretch it vertically by a factor of 1 on the deviation. And now the area will come back to 1. Because it's like saying we've got deviation times b, but then times h divided by the deviations cancel, we've got it back 1. So we also have to stretch it vertically. Now, stretching it vertically, what will that do to our equation? It now will get it back this one. So we've got that 2 sigma squared. It's almost the normal distribution that we want. But if you remember, we had this z minus mu as well. So I now need to shift the whole curve mu units. And once I've done that, I've got it back to that formula for the normal distribution. Again, this is something not to panic about. They're not going to ask you how you physically do it. But what that does is explains why, when we're working out z scores, we use this formula. Our standard normal distribution will be equivalent to any normal distribution if we use this substitution. So z will equal x minus mu over the deviation. So basically your score minus the average divided by the deviation. All right, so let's talk about the z scores then. So every normal distribution can be converted back to that standard one using that standardization equation of x minus mu over the deviation. The answer to that, or the result of that, is the z score. That's what's been appearing on those test reports I've been giving you since last year. And it basically represents that. The number of standard deviations the score is away from the average, above it or below it. And we usually give them to 2 decimal places. And that's probably because of those table of values, and when you're looking them up, it's like 2 decimal places. All right, well, what does this mean about quartiles and outliers when we're looking at data? Q3 then is 0.75. We know that because it's 75% of the data if we're starting from the left-hand side. So Q3, top 25%. So how much is in there? Q3 then must be 0.6745. I mean, if we look up the table of values, we can see which one gives us the answer of 0.75, and it's 0.6745. And then by symmetry then, because it's lovely and symmetric, we can work out Q1 must be negative 0.67. Interquartile range, Q3 minus Q1, will end up being 1.35. So that means for every standard normal distribution, the interquartile range is 1.35. Now, an outlier for any distribution, not only normal ones, but when we're looking at it, we say outliers are always greater than 1.5 times the interquartile range above Q3. That's for the top end. So if we plug those numbers in, we get 2.7. So basically that's telling me if you're more than 2.7 deviations from the average, then you would be considered an outlier of that data. And then by symmetry, of course, the lower end the same. So if your Z-score was less than minus 2.7, then that would be an outlier of the data. Let's look at some questions then. We're going to the chemist, we're going to get a prescription filled out. The time spent waiting for this prescription is normally distributed with an average of 15 minutes and a deviation of 2.8 minutes. What's the probability that the waiting time will end up being more than 20 minutes? Okay, so I'm going to let W represent the waiting time in minutes. Well, I've been told it's normally distributed. The average is 15. Now they told me the deviation, but remember in this notation, it's the variance we put there. So the variance is 2.8 squared, so 7.84. I want to know, when is W greater than 20? Well, I'll take it back to our standard normal distribution. So we'll convert it into Z-scores. So 20 would become 20 minus the average divided by the deviation. So we're saying, when is Z greater than, well, 25 on 14? Now, when we go back to our table of values, remember it's cumulative, it's actually less than, not greater than. So I actually want 1 minus the cumulative function of 25 on 14. So then it's just a matter of looking that up. And we can actually see, well, it's quite a low probability there, 0.03707, which is nice. We don't really want to be waiting more than 20 minutes. The TQ company. TQ, what's that stand for? Ah, it's a polite company. Yeah, of course, TQ. You get it? Thank you. Now, it makes a soft drink. This soft drink is sold in cans, 330 millilitres. The actual volume of drink. So there's going to be some machine that's going to shoot the liquid into the cans. Machines aren't perfect. They get it pretty good. Sometimes it'll get 330 mils, sometimes it won't. So the actual volume that ends up in the cans is normally distributed with a deviation of 2.5 millilitres. Now they want to make sure that at least 99% of these cans that they're going to end up selling does indeed contain, well, more than 330 millilitres. They don't want to rip their customers off, they don't want less than. So they want more than 330 millilitres. So that, what should they set the machine at? So should it just be 330, or should they put it on something bigger if they want 99% to get the right volume? So V is going to represent the volume of the drink that this machine's going to shoot out. In this case, we don't know the mean. That's what we're going to set the machine on, the average. We'll say, right, this is what we want you to send out. We do know the variance. So we want to know, when is V greater than 330? Changing it to the standard normal, that will become 330 minus the average we're trying to find over 2.5. Again, we've got a Z greater than situation. So what we're saying then is, when is the cumulative one equal to 0.01? Remember, we wanted it to be 99%. That leaves me 1%. So, all right, I want to know, when is it 0.01? Well, looking up at the tables, negative 2.33 gives me that answer. So now it's a matter of playing around with this and working out what the average turns out to be. So 335.825. So if we set the machine at 336 millilitres, there should be a 99%, at least a 99% chance that the cans are going to get the right amount of drink. Biologists collecting data, they like to do those sorts of things, biologists. They collect data on all sorts of weird things. And this one's going to be heights of a particular species of cactus. Very useful information. They've observed that 34.2% of the cacti are below 12 centimetres in height, but 18.4% of the cacti are above 16 centimetres in height. Now, assuming the heights are normally distributed, what's the average and the deviation of our cacti? So H is going to be the height of cactus. In this case, we don't know either bits of information. That's what we're trying to find. But if I convert it to Z scores, I'm going to say Z is less than 12 centimetres, so 12 minus mu over deviation. That's got to equal 0.342, 34.2%. The other bit of information we know is that Z being greater than 16 minus mu over deviation, that's going to have to equal 0.184. So my cumulative distribution, well, the first one's fine because it's already less than. That's got to come up with an answer of 0.342. The other one, well, that's greater than, so I'll look at the other side, and there's going to be 0.816 then, using the complementary event idea. Looking up in the tables, the first one, an answer of negative 0.41 will give us that result. The second one, 0.90 will give us that result. Basically, we've now got simultaneous equations. We should be able to find mu. We should be able to find our deviation. So we end up with deviation of 3.05. Subbing back in, there's our average 13.25.